Hi friends, welcome to Follow Up. Let's have a look at problem 2865 and 2866. So the two problems together. So this is called Beautiful Torus 1 here. So in this video for the two problems, so we're going to explain two methods. So one is based on a brute force and the other is based on using monotonic stack. So if you compare the differences between this problem, the Beautiful Torus 1, and the next problem, the Beautiful Torus 2, that is problem 2866, the difference lies in the constraint. So here the length of this list. So here is bounded above by 10 to the power 3, and the other one is bounded by 10 to the power 5, I guess. So in other words, we need to improve term complexity from Beautiful Torus 1 to Beautiful Torus 2. So with that said, let's continue. So here we are given a zero-indexed array called max heights of n integers. So we want to build n tors in the coordinate line. So the ith tor is built at the coordinate I and has a height of height I. So the main constraints are the following. So to be beautiful for a tor. So that is the height at index I is bounded above by this max height at index I. And the height is a mounting array. In other words, at this index I, it's peaked, right? So basically the left side is no larger than this height. And the right hand side is also no larger than this height. So we want to return the maximum possible sum of heights of beautiful configuration of tors. So for this problem, the main question is at which index we would like for the mounting array to be picked, right? So here we have three examples. In the first example, the return is 13. So here you can check different peaks. For example, if we use this one as peaks, so we want this 3 is already less than 5, but 4 is less than this. This 4 is larger than 3, so we want it smaller, so we get 3, right? In other words, we want to decrement this 4 by 1. But 1 is less than 3, and 1 is less than or equal to 1, so it's okay. So overall, this will be the total sum minus 1. The total sum will be 14, so minus 1, that is 13, right? So you can also try other indices as peak. For example, if we use this 4 as peak, so the right side is okay, but the left side we have 3. 3 is less than 4, it's okay, and 5 is not less than 3, so we need to decrement 5 by at least 2, right? So in this case, the sum of height will be the total minus 2, that is 14 minus 2, that's 12, smaller than 13, right? So similarly, you can use this method to examine example 2 and example 3. So notice that in example 1 and in example 3, so we have some repeated numbers. So this is also important. So for this problem, for Beautiful Torus 1, maybe this, due to the way we are going to code, it might be not that essential. But in order to solve problem 2865, it's essential to notice this part, right? So because this will help us to design algorithms to avoid mistakes. So again, so here we have this constraint, because this is very small, 10 to the power 3. Essentially, a n-square algorithm can pass, right? So here's this is the range, so not that important. So with that said, let's look at the first solution. So we are going to use brute force. So we want to check sum of height by using each index as peak, right? So the way we are going to do it is that if we fixed an index as peak, we want to know how much we should decrement at this each index and then get the sum. Then the corresponding sum of height will be the total sum minus that decrements, right? So this is our thought. Now let's first implement this this part and then do the second part. So here, hyperfunction. So I'm going to define a decrement function that's at index I. So in other words, if we use index I as peak, then how much amount should we decrement in total to make it a mountain array, right? So this, we are going to use a result that is 0. So we're going to increment this result. So current will be the max heights, right, at index I, right? And then we are going to check the left side and the right side to do this. So for index in range, so I minus 1, negative 1, negative 1. So this, we start from index I minus 1, and then we ending at 0, right? The increment is negative 1. In other words, we would decrement. So if the max heights at this index is less than or equal to current, so then we just continue, and then we for next comparison we want to set it to be max heights at index I. So this is the one. Otherwise, so if the max height index at IDX is larger than the current, we need to decrement that to be the current, right? So this is the smallest amount we can decrement. We should decrement. So this will be accumulated to the result. So max heights IDX minus current. So after we do the decrement, so the we want to set current actually to be the previous current, so we do nothing. If you like, you can do the current equals current logically, but you know, in the programming, so we do not need to change. So this is for the left side. Now let's look at the right side. Let's basically do this again, right? So what we want to do is we start from index I plus 1. So when ending at length of max heights, right? And then the decrement will be default to be 1. So similarly, if the max height is less than or equal to the current, so we just set the current, right? Otherwise, so we're going to do the increment for result, right? And then after we check the left and the right side, so we just need to return the result. So this function means that if we want to use index I as the peak, then this result will be the minimal amount we need to shrink or decrement to make it valid. So we want actually to get the smallest one. Then we just use the total sum minus this number. So this will be very simple, right? So now let's see minimal decrement. Let's use float infinity because we are going to find the smallest one, right? Then basically for I in range length max heights, right? Then we get the decrement. So decrement I. So we call the above function, and then the minimal decrement will be the minimal of the previous state and this D, right? So after this for loop, we actually can locate the corresponding minimum and decrement. So it's possible, you know, for different indices we have the same minimal decrement, but that's not essential for us because we are only care about to return the sum of the max heights, so minus this minimal decrement, right? So before we move forward, let's first do a test. Yeah, it passes the first example. So now let's look at the second, the generic case. Yeah, it passes all the cases. So for this problem, due to the assumption that the max height is 10 to the power 3, so it's okay for this method, right? So if you analyze the term complexity, so for each index, so actually we do a for loop essentially. So this is on, right? And then here, so each is on, so then basically this will be on square. So here it's 10 to the power 3, so your times square is 10 to the power 6. So for a typical computer, in 1 second, it can treat 10 to the power 7 operations, let's say units. So that's why it will be okay here. So now, in order to make this video shorter, so I'm going to explain the second part using problem 2866, that is Beautiful Towers 2. So essentially the two problems are no difference except the constraint, because in the second one, the n can be as long as 10 to the power 5th. So now let's end this video and move to next problem, the Beautiful Towers 2, and we explain the second method based on using monotonic stack. So with that said, that's it for this video. Thank you.